You slide your thumb across glass and launch an app. 2 billion calculations happen in silence. You open your camera and light bends through silicon smaller than a virus. You send a text that crosses an ocean in milliseconds, while atomic clocks in orbit measure time to the billionth of a second. Every single one of these moments relies on quantum mechanics, the physics of the impossibly small, where electrons acted. Like ghosts slipping through walls, and particles exist in two places at once. Your smartphone is not just a device, it's a quantum machine disguised as a slab of metal and glass. No one tells you this. But every transistor, every pixel, every stored photo depends on rules so strange that even the scientists who discovered them called it spooky. Your fingernail. Each one works because electrons tunnel through barriers that classical physics says they cannot cross. Flash memory traps electrons behind walls of silicon dioxide, 7 nanometers thick, using controlled quantum leakage. Your camera screen uses quantum dots that glow only because particles are confined to spaces measured in single nanometers. GPS satellites talk to your phone using atomic clocks that count over 9 billion quantum vibrations per second to pinpoint your location within meters. Random numbers securing your banking app come from chips that measure the inherently unpredictable behavior of photons to generate encryption keys that cannot be guessed. None of this worked 10 years ago. None of this should work by the old rules of physics, but it does, and most people have no idea why. Electrons don't orbit nuclei like planets orbiting a sun. They exist as probability clouds, simultaneously in multiple energy states until measured. Light acts as both a wave and a particle. And particles can pass through barriers that should stop them, a phenomenon called quantum tunneling, predicted by George Gamow and independently by Ronald Gurney and Edward Condon in 1928. These were not abstractions. These were measurements. Alpha particles escaping radioactive nuclei, electrons penetrating thin metal films. The math worked, even when intuition failed. If you value documented physics and engineering history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Nature Nanotechnology published March 2024 by Jixin Chen and colleagues at Queen Mary University of London, University of Oxford, Lancaster University, and the University of Waterloo demonstrating single-molecule transistors using quantum interference, and from IEE Spectrum's coverage, published November 2022, tracking how quantum tunneling now threatens traditional transistor scaling, but also enables new device architectures. Now back to the information. Make the gate smaller and transistors switch faster. Pack more transistors onto a chip and computers become more powerful. This principle, captured by Gordon Moore in 1965, drove the industry for 5 decades. The transistor in the Intel 4004 processor from 1971 measured 10 micrometers across. Modern smartphone processors from Apple and Qualcomm use transistors measuring 3 nanometers, a reduction of over 3,000 times. But there is a problem. At this scale, classical physics breaks down completely. Quantum effects take over. Its position is not fixed, but described by a probability function. When a barrier becomes thin enough, typically below 10 nanometers, there is a non-zero chance the electron appears on the other side without ever crossing the barrier itself. It simply materializes. For a MOSFET transistor, this is catastrophic. The gate oxide, the insulating layer that controls current flow, must be thin to improve performance, but cannot be thinner than about 1 nanometer or electrons tunnel through. Even when the transistor should be off, this leakage current wastes power and creates errors. The gate oxide thickness in their 14 nanometer and 10 nanometer nodes approached the 1 nanometer limit. Engineers introduced high dielectric constant materials like hafnium oxide to increase the effective electrical thickness while maintaining physical thickness, buying a few more years. But the tunneling problem persisted. By 2024, with 3 nanometer and soon 2 nanometer processes, the industry faced a choice: accept that Moore's law was ending or find a way to use quantum effects deliberately. Jixin Chen and colleagues built a transistor using a single zinc porphyrin molecule sandwiched between graphene electrodes. The channel was 1 molecule wide. The device switched on and off, not by raising or lowering a barrier, but by using quantum interference, where electron waves cancel each other out destructively when the device is off and reinforce constructively when on. The transistor demonstrated a switching ratio exceeding 10,000 to 1 and operated for over 100,000 cycles without degradation. The subthreshold swing reached 140 millivolts per decade, approaching the theoretical thermionic limit. Dr. James Thomas, lecturer in quantum technologies at Queen Mary, stated that quantum interference is a powerful phenomenon with potential for wide electronics applications. But single-molecule devices are still laboratory curiosities. The quantum effects already inside your smartphone are different, older, and far more brutal in their simplicity. Flash memory, the technology storing every photo and app on your phone, works entirely because of quantum tunneling. The mechanism was demonstrated in silicon devices in the late 1960s and applied to non-volatile memory in the 1970s. Eli Harari filed a patent in 1978 describing electrically erasable memory using Fowler-Nordheim tunneling through thin oxide layers. NAND flash, invented in 1988 by Fujio Masuoka at Toshiba, scaled this principle to billions of cells per chip. By 2020, a single flash chip contained over 1 trillion bits, everyone stored by trapping electrons through quantum mechanical tunneling. In the ground state, the floating gate holds no extra charge. To write a 1, a voltage pulse of around 15 to 20 volts is applied, creating an electric field strong enough to allow electrons to tunnel from the silicon channel through the oxide barrier into the floating gate. Once there, the electrons are trapped because the barrier is too thick for them to escape under normal voltages. The presence or absence of this trapped charge changes the threshold voltage of the cell, which can be read electronically. To erase, a reverse voltage is applied, tunneling the electrons back out. Retention time depends critically on oxide thickness. A barrier of 7 nanometers holds charge for over 10 years. 6 nanometers holds for 6 months to 6 years. 5 nanometers holds for 1 day. 4.5 nanometers loses 20% of charge in under 5 minutes. Quantum tunneling, which enables the write and erase operations, also destroys data retention if the barrier becomes too thin. The balance is razor sharp. Modern 3-dimensional NAND stacks over 100 layers vertically to increase density without shrinking the oxide thickness, a direct workaround to quantum mechanical limits. The sensor, whether CMOS or CCD, converts light into electrical signals using the photoelectric effect, a purely quantum phenomenon discovered by Heinrich Hertz in 1887 and explained by Albert Einstein in 1905, work that won Einstein the Nobel Prize in 1921. When a photon with sufficient energy strikes a silicon atom in the sensor, it can eject an electron, creating a measurable current. The energy of the photon must exceed the bandgap of silicon, about 1.12 electron volts. Lower energy photons pass through without interaction. Higher energy photons create electron hole pairs that are collected and counted. The bandgap itself is a quantum mechanical property. In a crystal lattice, electrons occupy discrete energy bands separated by forbidden gaps. Silicon is a semiconductor because its valence band, where electrons normally reside, is separated from the conduction band, where electrons can move freely by this 1.12 electron volt gap. Temperature, doping, and material purity affect the band gap, but its existence is purely quantum. Without it, silicon would conduct like a metal or insulate like glass, with no intermediate switching behavior. OLED panels use organic molecules that emit light when electrons transition between energy levels. QD OLED displays, introduced commercially by Samsung in 2022, add a layer of quantum dots, semiconductor nanocrystals, typically 3 to 10 nanometers in diameter. These dots emit light with a color determined entirely by their size due to a phenomenon called quantum confinement. An electron confined to a space smaller than its natural wavelength, about 10 nanometers for visible in the light energies experiences a change in its effective energy levels. Smaller dots have larger band gaps and emit blue light. Larger dots have smaller band gaps and emit red light. The size of the dot can be controlled during manufacturing with nanometer precision, allowing displays to produce pure colors across the spectrum, combined with red and green quantum dots. The blue light passes through the quantum dot layer, where it is absorbed and re-emitted at longer wavelengths, with over 90% of the Rec 2020 color space covered, wider than conventional OLED or LCD. The dots themselves are made from cadmium-free indium phosphide, avoiding toxicity concerns while maintaining color purity. Each quantum dot contains roughly 1,000 to 10,000 atoms, but behaves as a single quantum system due to confinement. The electrons inside do not occupy discrete atomic orbitals, but instead form a density of states determined by the dot's shape and size, a phenomenon first described theoretically in the 1980s and experimentally realized in the 1990s. These electroluminescent quantum dot displays have measured lifetimes of over 10,000 hours for blue dots and nearly 100,000 hours for green and red, though mass production remains several years away. The advantage over OLED is inherent. Quantum dots are inorganic and do not suffer organic degradation. Burn in the permanent ghost image left on OLED screens, becomes physically impossible because the dots do not chemically degrade under normal use. GPS navigation, another smartphone staple, depends on atomic clocks that operate on quantum transitions. Each GPS satellite carries 4 cesium or rubidium atomic clocks that define the second based on microwave transitions in cesium-130. 3 atoms. The frequency is exactly 9,192,631,770 Hz, chosen because this transition between 2 hyperfine energy levels in the cesium ground state is extremely stable and reproducible. The atomic clock continuously counts these oscillations to maintain time accurate within 1 second over 10 million years. GPS positioning works by measuring the time delay of radio signals traveling from multiple satellites to your phone at the speed of light. An error of just 1 nanosecond, 1 billionth of a second, translates to a position error of 30 centimeters. The satellites orbit at 20,350 kilometers altitude, where relativistic effects from both velocity and gravity alter the clock rates by about 38 microseconds per day, compared to clocks on Earth's surface. General relativity predicts gravitational time dilation causes clocks in weaker gravity to run faster, while special relativity predicts moving clocks run slower. The net effect for GPS satellites is a speed up. Without correcting for these quantum and relativistic effects, GPS would accumulate errors of over 10 kilometers per day. With gate lengths of only 6 nanometers that exploit extreme quantum confinement to achieve steep switching slopes, potentially breaking the Boltzmann tyranny, the fundamental limit on how much voltage a classical transistor needs to switch states. The devices use gallium antimonide and indium arsenide with a broken band alignment that allows electrons to tunnel between the valence band of one material and the conduction band of another. This band-to-band tunneling is only efficient when the structure is small enough that quantum confinement strengthens the electron wave overlap. Arian Afzalian at EMEC, not involved with the work, confirmed these results demonstrate steep slope, together with record drive current, and highlight the importance of small dimensions and extreme confinement. These are not transistors that will appear in consumer devices soon, but they prove that quantum mechanics, properly controlled, enables performance impossible with classical scaling. Traditional pseudo-random number generators use algorithms seeded by environmental noise like temperature fluctuations or user input timing. These appear random, but are ultimately deterministic and can be predicted if the seed and algorithm are known. Quantum random number generators use inherently random processes. ID Quantique developed a QRNG chip measuring 2.5 millimeters square that captures shot noise from a light-emitting diode using a CMOS image sensor. Photon arrival times are fundamentally random due to quantum statistics. The chip generates true random numbers from the first bit without accumulating external entropy. Samsung integrated this chip into the Galaxy A quantum smartphone launched with SK Telecom in May 2020. The device, a custom edition of the Galaxy A71 5G, became the world's first mass-market quantum-secured phone. By 2024, Samsung released the Galaxy Quantum 5, with expanded QRNG integration across banking apps, biometric authentication, and encrypted storage. The chip provides 200 megabits per second of certified random data, ensuring encryption keys cannot be predicted even with future quantum computers. SK Telecom partnered with DGB Daegu Bank and Standard Chartered to integrate QRNG into mobile banking apps, and CryptoNext developed a plugin for the Signal messaging app using quantum-generated keys. Gregory Raborti, CEO of ID Quantique, stated that with its compact size and low power consumption, the Quantus QRNG chip can be embedded in any smartphone to ensure trusted authentication and encryption of sensitive information. The chip operates by measuring quantum shot noise, the fluctuation in photon number due to the discrete nature of light, a phenomenon with no classical analog. If you value documented physics and engineering history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from IEEE Spectrum's November 2024 coverage of optical atomic clocks and positioning systems published by Dynag and Kina, and research by Inflection demonstrating portable quantum. Timing devices tested in flight in May 2024 at MOD Boscombe, down in the United Kingdom with Science Minister Andrew Griffith on board, plus findings from MIT News published November 2024 showing 6 nanometer transistors using quantum confinement to overcome silicon voltage limits. Now back to the information. The Apple A18 Bionic chip, fabricated by TSMC on a 3 nanometer process and released in September 2024, contains over 19 billion transistors. Each transistor has a gate length around 18 nanometers despite the 3 nanometer marketing label. The contacted gate pitch, the distance from one transistor gate to its neighbor, is 51 nanometers. The tightest metal interconnect pitch is 30 nanometers. These dimensions place the device firmly in the quantum regime. Electrons exhibit significant wave-like behavior. The channel length is only about 60 silicon atoms wide. Ballistic transport, where electrons travel from source to drain without scattering, dominates at gate lengths below 20 nanometers. Quantum confinement changes the effective mass of electrons in the channel. The density of states, the number of available energy levels for electrons, becomes quantized rather than continuous. Completely around the channel to maximize electrostatic control. The nanosheets used by Samsung and TSMC and the ribbon FET design from Intel improve the switching ratio and reduce leakage by ensuring the electric field controls the entire channel. Volume. Even so, at 3 nanometers, static power consumption from leakage current accounts for nearly 40% of total chip power at idle. Designers use multiple threshold voltage transistors, dynamic voltage and frequency scaling, and power. Gating to manage this. Without these techniques, a modern smartphone processor would drain its battery in under an hour, even when idle due to quantum tunneling leakage alone. Chip architects also exploit quantum effects deliberately through threshold voltage engineering. By adjusting the doping profile and work function of the gate metal, designers can shift the energy bands to tune how easily electrons tunnel into the E. Channel. High threshold voltage transistors minimize leakage for logic that does not need speed. Low threshold voltage transistors maximize performance for critical paths despite higher leakage. The balance is recalculated for every new process node as quantum effects become more pronounced. Spin-based electronics, or spintronics, uses the quantum spin of electrons rather than their charge to store and process information. Magnetic tunnel junctions, already used in MRAM memory, rely on spin-polarized tunneling, where electrons with a particular spin orientation preferentially tunnel through a barrier. Researchers at the University of Toronto demonstrated in 2025 that commercial CMOS transistors can form quantum dots when cooled below 77 Kelvin. At these temperatures, electrons become confined to discrete energy levels within the transistor channel, and applying a magnetic field splits these levels by spin, creating qubits. Soren Wojciechowski and his team measure qubit lifetimes and frequencies to understand how transistors built for classical computing can double as quantum processors simply by changing the operating temperature and environment. The work, published in Futurum Careers in June 2025, suggests that the billions of transistors already in smartphones could, in principle, serve quantum computing functions if cooled appropriately. Practical deployment remains distant, but the principle is proven. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, has been difficult to use because it lacks a band gap, but researchers at Georgia Institute of Technology, led by Walt Heer, reported in January 2024 that epitaxial graphene, grown on silicon carbide, substrates develops a band gap of around 0.6 electron volts with electron mobility 10 times higher than silicon. The key is controlled thermal annealings that aligns the graphene lattice with the substrate, creating flat terraces where electrons travel ballistically. Heer noted that this is distinct from other graphene bandgap methods which produce low mobility material. The team published their results in the journal Nature on January 3, 2024. Epigraphene can be nano-patterned and doped with precision, and its quantum mechanical wave properties are accessible even at room temperature, potentially enabling terahertz transistors that operate far faster than silicon. But back to the device in your hand right now. The battery uses lithium-ion chemistry, where lithium atoms intercalate between graphite or silicon layers in the anode. The diffusion of lithium ions through the solid electrolyte interface is a quantum mechanical process involving electron tunneling between lithium atoms and the electrode material. The charging curve, showing voltage versus capacity, reflects the density of states and quantum energy levels in the electrode materials. Fast charging protocols push current densities high enough that lithium plating, the deposition of metallic. Lithium on the anode surface becomes a risk. This is a quantum electrochemical process where lithium ions gain electrons and nucleate on the surface rather than intercalating into the bulk. Plating reduces battery life and can cause thermal runaway, the cascading failure that leads to fires. Battery management systems monitor voltage and temperature to avoid these quantum thresholds. Wireless charging uses inductive coupling, where alternating current in a transmitter coil creates a magnetic field that induces current in a receiver coil. The efficiency depends on mutual inductance and resonant frequency matching. At the microscopic level, the magnetic field is quantized into photons. though at the milliwatt power levels involved, quantum effects are negligible compared to classical electromagnetic theory. However, the semiconductors controlling the charging circuits, the MOSFETs switching the current on and off thousands of times per second, operate entirely in the quantum regime with gate lengths below 10 nanometers. Touchscreens use capacitive sensing, where your finger, a conductor, changes the electric field distribution across a grid of transparent indium tin oxide electrodes. The change in capacitance is measured by charging the electrodes and detecting current flow. At the atomic scale, the electrons in the ITO layer and in your skin interact through electrostatic forces described by quantum mechanics, but the macroscopic effect is well approximated by classical electrostatics. The controller chip processing touch data, however, runs on nanoscale transistors, where quantum tunneling and ballistic transport dominate. Audio codecs, the chips converting digital data to analog sound waves and back, use oversampling and noise shaping to achieve high fidelity. The delta sigma modulators inside these codecs push quantization noise to ultrasonic frequencies, then filter it out, leaving a clean audio signal. The comparators and integrators in the modulator are built from transistors operating at gigahertz speeds, with switching times measured in picoseconds. Quantum effects limit the minimum size and speed of these transistors, but clever circuit design works around these limits to achieve signal-to-noise ratios exceeding 100 to 20 decibels in flagship smartphone codecs. Encryption accelerators in the secure enclave of the processor use hardware implementations of AES, RSA, and elliptic curve cryptography. These algorithms depend on the difficulty of certain mathematical problems, like factoring large numbers or computing discrete logarithms. Quantum computers, if built at sufficient scale, would break RSA and ECC by using Shor's algorithm, which exploits quantum superposition and entanglement to factor numbers exponentially faster than classical algorithms. This threat has driven the development of post-quantum cryptography algorithms based on lattice problems and hash functions believed to resist quantum attacks. NIST published 3 post-quantum cryptography standards in August 2024, including ML-Chem and ML-DSA developed by IBM and partners. These algorithms are starting to appear in smartphone operating systems and secure messaging apps, preparing for a future where quantum computers threaten current encryption. Sensors using electrically detected magnetic resonance. Published in Nature Communications in December 2024, the work by Rugan Gang and Dane McCamey shows that organic semiconductors can detect magnetic fields without lasers or cryogenic cooling. The technique uses the spin states of electrons in the organic molecules, which are affected by external magnetic fields. Applying microwave pulses at the right frequency flips these spins, changing the current through the OLED in a measurable way. This could enable smartphones to map magnetic fields for medical diagnostics, identify material defects, or improve navigation using Earth's magnetic field variations. The technology remains experimental, but the proof of concept is established. Displays. The simulations model electron interactions in different molecular structures to predict how the materials will perform in devices. This approach, described by Scott Jenin, Vice President of Materials Discovery at OTI Lumionics, in an April 2024 article for Inside Quantum Technology, replaces physical experiments with digital simulations, accelerating development and reducing costs. The result is materials like the cathode patterning material used in next-generation smartphone displays, which allows the removal of notches and punch holes by patterning the OLED stack with micrometer precision. The quantum chemistry calculations underlying these simulations solve the Schrödinger equation for systems with hundreds of atoms, a task only feasible with advanced algorithms and high-performance computing. Photonic integrated circuits, chips that route light instead of electricity, are being developed for data centers and telecommunications. These circuits use silicon waveguides and modulators that encode data onto optical carriers. The underlying physics includes quantum interference in multimode waveguides, quantum efficiency in photodetectors, and stimulated emission in semiconductor lasers. NVIDIA's Spectrum X photonics platform targets 100 to 400 terabits per second throughput using silicon photonics. While these systems are not yet in smartphones, the trend toward optical interconnects and high-performance computing will eventually trickle down to mobile devices as data rates increase. Quantum tunneling to image surfaces at atomic resolution. A sharp metal tip, often tungsten or platinum iridium, is brought within a few hundred picometers of a conductive surface. At this distance, electrons can tunnel between the tip and surface even though they are separated by vacuum. The tunneling current is exponentially sensitive to distance, changing by an order of magnitude for every angstrom of separation. By scanning the tip across the surface and measuring current, the microscope maps atomic positions. This technique revealed the structure of silicon surfaces, graphene layers, and individual molecules. The same physics that enables scanning tunneling microscopy, the probability of electrons tunneling through barriers, is what limits how small transistors can shrink and what allows flash memory to store data. Modern fabs use extreme ultraviolet lithography at 13.5 nanometer wavelength to pattern features smaller than the wavelength of the light itself. This is possible because the photoresist, a light-sensitive polymer, undergoes quantum chemical reactions when exposed to EUV photons. Each photon has an energy of 92 electron volts, far exceeding the bond energies of organic molecules, allowing precise chemical patterning at nanometer scales. The EUV light is generated by focusing a high-power laser onto a tin droplet, ionizing it into a plasma that emits EUV radiation. The plasma temperature reaches millions of degrees, and the photons are collected by multi-layer mirrors made from alternating layers of molybdenum and silicon, each layer precisely 14 angstroms thick. The mirrors rely on constructive interference, a wave phenomenon, to reflect EUV light efficiently. The entire system, from plasma generation to photoresist chemistry to mirror coatings, operates at the intersection of quantum mechanics, optics, and materials science. These facilities are among the most complex machines humans have ever constructed. Inside them, photons, electrons, atoms, and molecules interact under conditions of extreme precision. Temperatures are controlled to millikelvin, pressures to millibar, alignments to nanometer, and chemical purity to parts per trillion. Every step, from ion implantation to chemical vapor deposition to atomic layer deposition, is governed by quantum mechanics. The transistors they produce work because engineers understand and control these quantum processes with ruthless precision. You send a message and it delivers. The 10 billion transistors, the quantum dots, the atomic clocks, the tunneling electrons, the random number generators, the confined photons, all of it hums in silence. The device feels solid, predictable, mechanical. It is none of these things. It is a quantum system held together by engineering, a machine where every operation depends on particles behaving in ways that defy classical intuition. In May 2024, Inflection flew a portable optical atomic clock called Ticker aboard an aircraft at MOD Boscombe Down in the United Kingdom. The clock, about the size of 3 pizza boxes, used ytterbium atoms cooled to near absolute zero to measure time with femtosecond precision. Andrew Griffith, UK Science Minister, was on board. The flight tested whether quantum timekeeping could replace GPS in environments where satellite signals are jammed or spoofed. The clock outperformed all onboard references, proving that quantum technology can function in real-world conditions. Judith Olson, head of the Atomic Clock Project at Inflection, confirmed that briefcase-sized optical clocks will shrink to toaster size within a few years, enabling GPS-independent navigation for aircraft, ships, and eventually consumer devices. The physics is the same, trapping atoms in optical lattices, exciting them with precisely tuned lasers, and counting quantum transitions. Few cubic centimeters, these use vapor cells containing rubidium or cesium gas and coherent population trapping, a quantum interference effect, where 2 laser beams drive the atoms into a dark state where they no longer absorb light. The transition frequency serves as a timing reference accurate to a few parts, in 10 to the 11th. These clocks are already used in military devices and telecommunications infrastructure. Within 5 to 10 years, similar clocks could appear in smartphones, providing GPS-level timing without satellite signals. The barrier is not physics, but cost and power consumption. The latest systems from IBM, Google, and IonQ use thousands of qubits, but still require millikelvin cryogenic cooling and operate with error rates high enough that useful computation remains limited to specialized tasks. IBM's Condor processor, announced in November 2023, has 1,121 qubits. Google's Willow chip, demonstrated in 2024, achieved exponential error suppression using quantum error correction with superconducting qubits. But even these systems are sensitive to noise, vibration, magnetic fields, and temperature fluctuations. A smartphone environment, with its thermal cycling, electromagnetic interference from radios, and constant motion, is hostile to delicate quantum states. Still, the trend is clear. Quantum systems that once filled rooms now fit on chips. The transistors in your phone already exploit quantum effects that were lab curiosities 30 years ago. The quantum sensors, the atomic clocks, the random number generators, all of these are migrating from research to product. Intel, Cisco, and Broadcom all produce photonic transceivers for data centers. The waveguides are etched into silicon using the same lithography tools that make transistors. Light propagates through these guides with minimal loss. and modulators encode data by shifting the phase of the optical carrier using the plasma dispersion effect, a quantum phenomenon where free carriers in silicon change the refractive index. Photodetectors convert light back to electrical current using the photoelectric effect. The entire system operates in the telecom bands at 1,310 and 1,550 nanometers wavelength, chosen because silicon is transparent at these wavelengths, and optical fiber has minimum loss. Data rates exceed 100 gigabits per second per channel, with dense wavelength division multiplexing allowing dozens of channels on a single fiber. These photonic links will eventually reach smartphones as video streaming and AI processing demand higher bandwidth. Clothing and biological tissue without ionizing radiation. The challenge is generating and detecting terahertz waves efficiently. Quantum cascade lasers, semiconductor devices using intersubband transitions and quantum wells can emit at terahertz frequencies, but require cryogenic cooling and consume milliwatts of power. Room temperature, terahertz sources based on graphene plasmonics and resonant tunneling diodes are under development. If solved, terahertz imaging would add a new sensory modality to smartphones, seeing through materials opaque to visible light. Below 5 nanometers, quantum effects dominate so thoroughly that devices stop behaving like classical switches. Variability from atomic scale roughness, random dopant fluctuation, and line edge roughness becomes unmanageable. Each transistor differs from its neighbors because the placement of individual atoms matters. Manufacturing tolerances measured in atoms are not achievable with current lithography. The industry is pivoting to three-dimensional integration, stacking logic, memory, and analog circuits vertically with through-silicon vias connecting them. TSMC's CoWoS packaging and Intel's Foveros technology already stack dies at micrometer pitch. Future systems will stack thousands of layers, each with billions of transistors, creating computing volumes rather than computing surfaces. But even this has limits. Heat dissipation, signal propagation delay, and quantum noise set boundaries that clever engineering can push but not eliminate. The quantum tricks that make them work, tunneling, confinement, interference, superposition, will be even more central as devices shrink. Engineers will exploit new quantum phenomena, spin, topology, entanglement, but the fundamental weirdness remains. Particles that act like waves, electrons that tunnel through barriers, photons that arrive randomly, energy levels that are quantized. None of this is optional. It is the physics of small things, and small is where all the action happens. Your phone is not a quantum computer. It is something stranger, a classical computer built entirely from quantum parts. Every calculation, every image, every sound, every connection depends on electrons and photons obeying quantum rules. Most of the time, these rules are hidden. The device acts deterministic, predictable, reliable, but underneath, the world is probabilistic. Electrons exist in superpositions until measured. Photons interfere with themselves. Atoms jump between energy levels without passing through the space between. The illusion of solidity and certainty emerges from trillions of quantum events orchestrated with nanosecond precision. The revelation is this: quantum mechanics is not some esoteric theory confined to labs. It is the operating system of reality at small scales, and those scales are the scales that matter for every device we depend on. The smartphone is not a glimpse of the quantum future. It is the quantum present, hidden in plain sight. 10 billion transistors in your pocket, all dancing to rules that break common sense. You swipe, you tap, you scroll, and the quantum world responds, every time. The devices achieved steep switching slopes by exploiting quantum confinement and band-to-band tunneling. This is not about longhouses or Viking graves. This is about electrons confined so tightly their energy levels quantize, changing the density of states and enabling tunneling at lower voltages. Arian Afzalian at IMEC confirmed the work significantly improves tunnel field effect transistor performance, demonstrating steep slope with record drive current. The dimensions are extreme. 6 nanometers is 20 silicon atoms across. At this scale, electron wave functions overlap, quantum interference matters, and classical transport models fail completely. Flash memory using Fowler-Nordheim tunneling, demonstrated by Eli Harari in 1978 and commercialized by Toshiba in 1988 with NAND flash. Quantum dots using size-dependent bandgaps, theorized in the 1980s and commercialized by Samsung in 2022 with QD OLED displays. Atomic clocks using cesium hyperfine transitions, standardized in 1967 and orbiting Earth and GPS satellites since 1978. Quantum random number generators using photon shot noise, developed by ID Quantique in 2001 and integrated into Samsung phones in 2020. Transistors exploiting quantum tunneling, both as leakage problem and as deliberate mechanism, evolving continuously from 1960 to today. The quantum world is not distant or abstract. It is immediate, tangible, functional. Every tap, every swipe, every photo, every search query runs on quantum mechanics. The physicists who discovered these effects, Planck, Einstein, Bohr, Heisenberg, Schrödinger, would be astonished to see their equations etched into silicon, running apps, streaming video, encrypting messages. They proved the math worked. Engineers proved the math could be built, and now 10 billion people carry quantum machines without knowing it. The next step is using quantum effects deliberately for computation, not just for switching. Qubits instead of bits, superposition instead of binary states, entanglement instead of wires. That will take decades, but the groundwork is being laid. Silicon qubits and CMOS transistors cooled to millikelvin, topological qubits and nanowires, photonic qubits and integrated waveguides. All of these use the same fabrication tools that make your phone's processor. The device you carry today is a milestone, the first mass-market quantum machine that nobody recognizes as such. It works because electrons tunnel, photons interfere, atoms vibrate, particles confine. It works because physicists cracked the quantum code and engineers turned that code into technology. 15 years ago, none of this was possible. 15 years from now, it will seem primitive. But right now, in this moment, your smartphone represents the apex of quantum engineering disguised as consumer electronics. And somewhere, buried in silicon and glass, 10 billion quantum events happen every second, turning probability into certainty, weirdness into function, and physics into magic. You cannot see it, but it is there. It always has been. Quantum mechanics is not the future. It is the present, humming in your hand.